Hello guys, hope all of you are doing great. In the previous part of the video, we have seen how we can display a single character on the screen as well as how we can display a string on the screen. And towards the end of the video, I mentioned one problem like what if we want to display the content of a register as it is on the screen? What I mean is, say, for example, if say in AX register we have this value, say um, say 105, and we want to display this value on the output screen as it is 105, not its equivalent ASCII code. Okay, say the equivalent ASCII code is, say, for example, it is lowercase e, and it is not E actually, it might be EF or something, whatever. Just for the sake of an example, I'm saying that the equivalent one is E, and now till now what we know is that first the value will be converted to its equivalent ASCII code, and that code will be displayed. This we know, like how to do this. But what if we want to display this as 105 as it is on the screen? So that problem we talked about. Now, see, one thing you should realize, like say, for example, you consider C programming language. There we have a variable A, and there 105 is there. Then printing the value of this A on the screen is very simple in C programming language. You just have to write printf, print %d, and the value of the variable A. This particular instruction will display 105 on the screen. One instruction, right? Or one statement. But in 8086 programming, if we want to do that, actually things are not that simple. Simple in the sense, not simple in the sense we have to write actually a few more lines of code actually to display to achieve this thing actually. One particular line of code is not going to do the job. We have to write a set of instructions. We have to execute a set of instructions one after another to achieve this goal. And to do that, actually, we have to learn a few more things before actually, we being able to do that. So for that reason, what am I going to do is I'm going to, obviously I'll be writing the program, but I'll be writing the program in the most probably the next video or maybe in the next to next video. But in this two or one videos, what we're going to do is we're going to learn the necessary concepts that we need to know actually to solve that problem. And one of the most important concept out of all these is this conditional or unconditional branching or jumping. This one you can think of like, sort of equivalent to the if else statement. See here, like use in C programming or any high level programming language, we have these if else construct. And what is the main, what is the goal of those if else statements are like branching, right? That is what we do typically is we check a condition, and based on the result of the condition, if the result is true, then we execute a one block of code, and if the result is false, then we execute another block of code, and at the end both the path of execution actually merges like this. So yeah, these lines you can think of like these arrow lines, you can think of the flow of control. It means the flow of execution. The execution goes from top to bottom, and at this point it checks a particular condition, and based on the value of the condition or based on the result of the condition, it will either move, the execution will either take this path or it will take this particular path. And then at the end, after executing any one of these block of code, again it flows normally like that. Now this is what more or less happens in high level programming language like C. Now the same thing if you want to do, or if you want to achieve in 8086, then what you have to do is you have to make use of those conditional or unconditional jumping or branching instructions. Okay, and okay, before actually writing the code, let me show you or let me like sort of explain you the concept slightly. So what you can think of is right, when you write an assembly code, a 8086 program, then what happens? The program itself is stored in the code segment, isn't it? You know that thing. And the starting address of the code segment is stored in the CS register, and it points to the starting of the code segment. And inside that code segment, you can think of like this code segment memory block is actually split into some bytes. So this is byte number 0, byte number 1, byte number 2, byte number 3, byte number 4, like that. And each instruction is stored like on these bytes. See here, for simplicity I'm assuming that each instruction is of 1 byte. So this is instruction 1, or I'm writing here instruction 0, instruction 1, instruction 2, like that. So here all my instructions are sort of 8 bits long, but it might happen. See here, let me show you one thing here quickly. Say for example, I'm showing you this is the this is a program. Just assume it's a 086 program. Most probably this is the program that we wrote in our previous part of the video, but really it doesn't matter. My point is, see here inside code segment at byte number 0000, this particular instruction is stored. It means the opcode of this particular instruction is stored. And then at byte number 3, it means, see here, the length of this particular instruction is of the 0th byte, the first byte, and the second byte, 3. The length of this instruction is 3 bytes. Similarly, at byte number 3, or from byte number 3, this next instruction is stored. From byte number 5, this particular instruction is stored. Like that, these instructions are stored consecutively, one after another, like that. Now see, here for simplicity, I'm assuming that, okay, each instruction is of 1 byte, and then they are stored. These instructions will be stored in the code segment one after another, like this: I1, I2, I3, I4, and like that. Suppose this is IN. This is the nth byte, and this is the IN instruction. And also, one thing you need to know is that when we execute a program, say for example, till now you have seen many a times executing program in debug mode, and what you saw typically is these instructions are executed one after another in a sequential way. It means first this instruction pointer will be pointing to the first byte. I mean, it will be pointing to the first instruction. It will have the byte number of the first instruction, and then once that instruction is over, immediately IP will point to the next instruction, whatever the byte number, starting byte number of that instruction is. Right, and this is the typical flow or default flow of the program. Default flow of the program in the sense like it will always be executed from top to bottom, one instruction at a time. Once this instruction is over, then it will be executed. Then once this is over, then this instruction will be executed, and once it is over, then this instruction will be executed, like that. Okay, and so that is actually sort of the default flow of execution. But what we might want to do at some point of time is, or what we do usually in this conditional branching or unconditional branching, mainly in branching, is say if from some point of these like from some of these instructions, say for example at some point of time these the ith instruction is actually getting executed. And what we might want to do is that from this instruction, once this instruction is over, instead of transferring the control to the next instruction, that is I+1 instruction, what we can do is actually we can set our instruction pointer to point to any other instruction other than this default next instruction. Say we can set our instruction pointer to actually point to, say for example, this second instruction one more time. It means what? Like suppose this is a program and it is getting executed, like I0 is executed 1, 2, 3, 4, 5, 6, like that it is executed, and then at some point of time it is executing this ith instruction. And the instruction is written in such a way that what it does is it sets the instruction pointer, the value of the instruction pointer to 2. To in the sense like this address, and then what happens is in the next clock cycle this instruction will be executed. I mean, whatever, as we know, right, what this instruction pointer points to, it points to the instruction which is to be executed next. So if we set the IP instruction pointer to set to 2 or to point to 2, instruction number 2, then obviously the next instruction will be executed, that will be executed is I2, not I+1. This thing is actually called as uh, branching. And how do you do that actually? See, and directly if we see here, now here when we transfer the control from this point to this point, this might happen at least in two different ways. One thing is like without checking anything, without checking any condition, just simply we might transfer the control or set the IP to point to this instruction to, or based on some condition actually, we might sometimes want this IP to point to 2, or sometimes we might want this IP to point to some other instruction. See here, it is not needed that whatever it points to, it always has to point to some previous instruction. It might happen that it actually points to some instructions which are stored after this IAT instruction. This also might happen. Now see here, my point is this branching, this transferring the control is called as this branching, but this branching might happen in two different ways. Either one is your unconditional branching, that is as the term itself indicates, like unconditional, without checking anything, without checking any condition, we simply sort of hard code the transfer. Another one is like we might do this branching based on the the result of some execution, in sort of in a dynamic way. Whatever the result of execution is, based on that, we might sometimes want to transfer the control to a different point, and then at some other situations we might want to transfer the control to a different point. So this sort of transferring or branching is called as your conditional, I mean based on some condition, conditional branching. Okay, so that is more or less the idea. But we are now ready to write the code. But for that, let me tell you one more thing here. See, one point of interest, that see what we want to do is we want to set mm, instruction pointer. We want to set the flow of execution to a different location. We want to transfer the flow of execution to a different location. So programmatically, if we want to do that, the first thing that we have to do is whatever the instructions we might want, whatever the instruction to which we might want to transfer our control, those instructions we have to actually give some name. Say for example, this is one instruction where we might want to transfer our control at some point of time, so we actually can give a name to this particular instruction, so that using this name we can actually refer to the byte number of this particular instruction. And this naming process is called as your labeling, or these names are called as your labels. Okay, now once we know more or less these things, then we are ready to write codes. Let's first write a simple code and see how these branching actually works. Let's say I already have written this basic skeleton of the code, and there what we want to do is let's make use of this branching thing. Say for example, I move to AX register the number 3 hexadecimal, and say for example move to BX register 4 hexadecimal. So these are my two instructions, and after that here what we want to do is at this point, see here, if we execute this program, how it will be executed. It will first copy the starting address of, or the offset of data segment to AX. From there it will copy it to DX, and then 3 will be copied to AX. See here, it is coming from top to bottom, one instruction at a time, and then 4 will be copied to BX, and after that obviously the next instruction is this one, that 4C will be copied to AH. But say for example, here what we do is we want to, after executing this particular line, again we want this particular instruction to be executed. Okay, that is, see here, after executing this instruction, by default obviously this is next instruction, but what we want is we do not want this one to be executed after this particular instruction. We want again this particular instruction to be executed. Then how we can do that? Obviously we can do that using the concept of branching. Now see here, I'm going to show you unconditional branching. So, okay, after executing this move bx, 4h without checking any condition, we want to transfer the control to this instruction, which is at line number 9. Say this 9 is not related to the program. Okay, I'm just saying you to just to indicate which line I'm talking about. This 9 is a feature of Visual Studio Code, and these are instructions. Nothing to do. This 9 has nothing to do with this instruction. Don't you, uh, misunderstand me. The point here is that, okay, here we want to transfer the control to this particular instruction. So for that reason, we can make use of this unconditional jump instruction, JMP. This is called as unconditional jump instruction. This instruction actually transfer the control, or you can say like this instruction actually sets the instruction pointer to a particular address. You can think it that way. Okay, so if it is the case, it means what? Here we have to write an address, memory address. But yes, that is true. We have to write here a memory address. But the thing is, instead of writing, because we do not know what address this particular instruction will have exactly, right? So for that reason, what we have to do is we have to actually assign a label to this particular instruction first. So we'll be giving it a label. So for example, I'm calling it L1 colon. The syntax of writing the label is the name of the label and then this colon. And after that, you can write the instruction. Or for clarity, if you want, you can write the instructions from the next line. So this is how you give a label. So L1 means you are actually talking about this particular, you are giving a label to this particular instruction. Okay. If it is the case, then with this jump instruction, what we can do is we can simply write the level where we want our control to be transferred. So if you see this program, what it looks like is like, okay, it will be executed from like here. It will first copy the starting address to AX, then these AX to DS, then this L1. This is not an instruction. It means like like it for the program. It's sort of this thing is not visible. Okay, and then it will copy 3H to AX, 4H to BX, and then jump L1. The assembler will actually convert this L1 to the proper address. So that way this jump instruction will set the control, set the instruction pointer to point to this particular instruction again, L1. And again, the flow of execution. It means again it will be this instruction will be executed. After that, this one will be executed, and again this particular instruction will be executed. This instruction is again going to set the instruction pointer to this one, and that way you can think like, okay, now see here. If you think for a moment, then what will happen is if you execute the program will continuously execute these two lines again and again and again and again. So that way the flow of execution will never reach this point, and that way this program is never going to end actually. You should comprehend that. But anyhow, although it is not going to end, let's execute this program in debug mode and see, let's see whether we understood the thing in the right way or not. Okay. Okay, then so what am I going to do is I am going to compile this program. First, I'll exit from here. And then the name of my program here is, as you can see, pp8.asm. pp8.asm. Okay, so I'll be compiling it, tasm pp8.asm, and no error, no warning, so we're good to move. So link pp8, and then in debug mode pp8. Now if we do that, let's see here what happens. Move AX, 48AE. 48AE is the starting base address of the data segment, and then that will be copied. I'm pressing F7, it is copied. Then DS will also have the same value here, and then 3 will be copied to AX, and 4 will be copied to BX, and 5 will be, now see, the next instruction is after copying 4 to BX, jump L1, and here it is jump 005. See here, where we put this L1 against this move AX, 3H. And see here, what is this 005 address pointing to? It is pointing to move AX, 0003. I mean, this particular instruction. So jump L1 is nothing but actually jump to that particular instruction. Now see here, right now the instruction pointer is 000B. It means this 000B. It means what? This is the instruction which will be executed next. Now, as soon as I execute this instruction, like once this instruction is over, I'll be, then you just have a, keep your eyes here, like what value this instruction pointer actually, will have after the execution of this particular instruction. So I'm going to press F7 at the count of 3, which will make this instruction to be executed, and then it is going to change this IP value. As a result, the IP value is going to change. Okay, so just keep your eyes here and see how this IP value changes as soon as I press this F7. Okay, 1, 2, 3. Sorry, 1, 2, 3. See here, this IP is actually 0005, which is nothing but this instruction again. It means, see here now, since IP is 0005, it means whatever it is the instruction which is there in this particular byte, that instruction will be, or starting from this particular byte, that particular instruction will be executed. So, okay, right now it is 5. I press F7 and then it is executed, and immediately IP is modified to point to the next instruction, the default next instruction, which is 8. After 5, the next instruction is from 8. So it will be executed. Again, I'm pressing F7, and then you can see that then this IP will be, it will be pointing to the next default instruction, which is B. 1, 2, 3. This is pointing to the next instruction. But here, see, if I execute this, now it is not going to point to D. It will be pointing to, IP is not going to point to D. It is going to point to 0005, which is this instruction. So, as I said, now the program is sort of, it will go round and round and round, and it will continuously execute these 2 or 3 lines of code again and again and again. So that way, this program is sort of an infinite loop. Don't worry, this is not coming because of this infinite loop. It is some other error. But anyhow, I guess if people got the idea, like what this jump instruction is doing. Okay. Now, let's come back to this point here. Now, this jump, when you write jump like in this way, this particular jump instruction is actually called as I said, unconditional jumping. Why it is so? It is unconditional jumping in the sense, like here, see, this jumping always happens. No, I mean it always happens without any without checking the value of any other thing. It just happens as soon as the control reaches here. It executes this instruction, and again it sets the IP back to this particular instruction. So that's why it's an unconditional jump instruction. But since unconditional jump is there, certainly you will be, yeah, that is right, whatever you're thinking. So certainly there will be something called as conditional jump also. Now, what is this conditional jump? It is conditional jump in sort of these, these if else thing that I said. Conditional jump. I mean, if it is true, if a certain condition is true, then we'll be executing, we'll be jumping, or we'll be transferring our control to a different block. If certain condition is false, then we'll be transferring our control to a different block. This way you can think, or you can think this way. So here in conditional jumping, based on the output or based on the result of the condition, either we will be transferring our control to a, we might want to transfer our control to different locations actually. Say for example, in what situation it could be useful. Say for example, you just consider, yeah, you are right if you're thinking it that way. Say you have to write a program to check if a number is a positive number, negative number, or 0. Say, just assume, we have to write a program to do this thing in 8086, okay? Then how we can do that actually? See here, this conditional jumping is going to be useful. Now, how do we know like whether a number is positive, negative, or 0? Yeah, one way is that, yeah, in C programming, we'll be doing it in this way. Like if that particular number A is greater than 0, then we'll be writing, okay, that number is, positive. And otherwise, this is not the exact syntax of C programming. Don't you think like that? I'm just writing it. Else, if A is less than 0, it means the number is negative. Otherwise, if it is not positive, it is not negative, then certainly it will be 0. It is as straightforward as this to write this code in C programming or any other high-level programming language in that case. But in 8086, how we can achieve that? See, yeah, certainly in 8086 also we can do this sort of comparison. But let's see, instead of doing comparison, we'll try to do it in, using, say, for example, subtraction. Now, I'm talking here, right now I'm talking about conditional jumping. And when I say conditional jumping, as I said, now based on some conditions, we might want to transfer the control to different blocks. Now, what conditions those are actually? Mainly those conditions are actually we check, like the different flag values of the flag register. You remember the flag register? In this flag register we have different flags. Say for example, zero flag, we have sign flag, we have auxiliary flag, we have overflow flag, parity flag, direction flag, or I guess index flag, draft flag. Okay, those are some 8 flags there, right? Now, some of the common flags are like the zero flag or carry flag is there, right? Don't you, how can I forget that? Now, these flags actually represents a certain state, of the result of the previous, instruction. Say for example, if the result of the previous instruction is 0, then this Z flag will be set to 1. If the result of the previous instruction is negative, then this set flag will be 1, which will indicate that the result is negative. If it is 1, that will implies that the result is 0, like that. So if there is a carry, suppose you are performing addition operation, okay, and then there is a carry from the most significant bit, then this carry flag will set to 1. So we know, right, these flag registers actually reflects different states of the result of the of the previous instruction. Now, when we do a conditional jump, actually we just do the jumping with respect to the values of some one or more these flag registers. Okay, what I mean by that. Let's say, let's talk about this particular program. Write a program to check if the number is positive, negative, or 0. How we can do that actually? See, one simple approach I'll be telling you here. Say we want to check if the number is positive, negative, or 0. Say the given number is, for the time being, you consider the given number is there in A. So what we can do is we can make use of not A, say sorry. Say the given number, sorry. Just a second. Say the given number is there in the AX register. Okay, it is in AX register, and what we do is we subtract this AX register. I mean, from this AX register, we subtract 0. We And how we can do that in 8086, we can make use of this subtract instruction, AX comma 0. You know this subtract instruction, what does it do? It will actually, you can think this instruction as this: AX is equal to AX minus 0. Whatever it is the value of AX register, from there 0 will be subtracted and the result will be stored back in this AX register. Now we know, like see here, say for example, uh, let's see actually how this subtract instruction changes the values of the flag registers. Okay, then we will be actually make use of this conditional jumping. Let's first see how this subtract changes the content of the flag registers. Now see, subtract is not the only one instruction that is going to change the content of the flag registers. It could be any other instruction actually. Okay, subtract I'm just using as an example. Let's see that. Say for example, we have now we do not. I'm erasing these labels for the time being just to make it clear. So for example, assume that we have in AX register a number which is 5, say. And then in BX register, we have another number, say 3. And then we perform this subtract instruction, subtract from AX, BX. It is like we are performing actually AX minus BX. Let's see what happens when we execute this particular instruction. We will be going there, we will be storing this. See, in your case, you have to save the file. Sometimes this thing gets happened. Just a second, we'll be ready in a moment. Yep, right. So we have to compile tasm pp8.asm. There is an error. Too few operand instruction pp8 line number 10. Line number 10 here. Okay, this is a mistake. I didn't put the comma. So done. And then again, let me compile the program. This time no error. Then t-link pp8 and then td pp8. We want to see the program in the debug mode. Okay. So I'm executing it in debug mode, and then let's execute it. I'm pressing F7, copying the starting address to DS, then now moving it to DS, 5 to AX, 3 to BX. Then now our instruction of interest is subtract AX minus AX comma BX. Okay, and right now these are the contents of the flag registers. As soon as you perform AX minus BX, you can see AX is 5, BX is 3. So 5 minus 3 is 2. Obviously, in the result will be stored in this AX register as 2. And also you can see here, some of the flags will change. Here, see, sign flag will not set because 5 minus 2 is a positive answer. So sign will remain 0. 5 minus 3 is not 0. So 0 flag again will remain 0. 5 minus 3, there is no carry. Carry will remain 0. I think most of the flags will remain, unchanged here. So it is 2, and most of the flags are unchanged except I guess this I pointer is set to 1. But that is this flag is right now we are not interested in this flag. We are mainly interested in CZS, these three flags. Okay. Now this is a normal operation, so I was just thinking it will happen. Just a second. Here, okay, just a second. What my point? Okay, let me change the value of these registers. Say for example, now it is 3, AX is 3, BX is 5 here. And if we perform now the subtract instruction here, this time you will be seeing the changes sort of. Again, it got hanged. I'm sorry. Tasm pp8.asm and then t-link pp8 dot, sorry, that is not it, and then td pp8. Okay. Now pressing F7, let's do the copying and then subtract AS comma BS. Right now, these are the content of the flag registers. We are performing AX minus BX. AX is 3, BX is 5. So 3 minus 5, the result will be negative. So you can see that the sign flag will be set to 1. Here, just keep your eyes here. It is 1 here. Okay, and see the result. Where the result will be stored? The result will be stored in AX register. And see the content of the AX register. It is FFFE. You might be thinking you are actually expecting a 2 there, but why this FFFE is coming? See here, if it is a negative number, then the number will be stored in the form of 2's complement. So if you take the 2's complement of FFFE, you will get a 2. I just leave the thing as sort of for you people. You just if you want you can double check that. Okay, but my point here is that you see here, and also you can see this carry flag is also set. I mean, carry flag set is indicating that okay, there is a borrow actually in the most significant bit. But my point of interest here is this sign flag. See, as soon as we subtract a big number from a smaller number, you can see the sign flag is on. It means indicating that the result is a negative result, right? Now let me change again the values of these AX and BX to have equal numbers, 3 and 3. Now this time if we subtract, this time if you again it got hacked. What is happening? Okay, maybe for this reason I have to complete it. Okay. Oh, no, even not for that reason. I don't know. I'm just restarting it again. pp8.asm. What I did is I changed these the value of the of of both the registers to be same, and then we're performing this subtraction operation. So we will be seeing here, this is your program, and I'm pressing here F7, copying the value, equal values A and B, and then subtracting AX minus BX. Now, if we perform AX and BX, you can see the result in AX, it will be 0, certainly. And also, you have to look here, the Z flag will be set to 1, indicating that the result of the instruction is 0. So here, just keep your eyes here. As soon as I press F7, you should see a 1 here. You should see a 0 here. Okay, just these two, if possible. Keep your eyes together on these two, content. So here, now it is 0 and it is 1. So that way, now see, what we just learned is that, okay, the execution of a particular instruction can actually change the content of these flag registers in a meaningful way. See here, just by looking at the flag registers now, we can take some decisions. Say, now we are ready sort of to write this program at least. Write a program to check if a number is positive, negative, or 0. So what we can do basically is, if we have to write this number, see, this is the program that we want to write. Uh, see, write a program, this program we want to write. Let me copy it and paste it here. Okay, this is the program that we want to write. Write a program to check if the number is a positive number, negative number, or 0. So what we can do is, one way of doing this, or one way of writing this program is, we can copy whatever that number is. Say, for example, that number is 5. So we copy that number to AX register. Say, whatever that number is, say 5. This is the number that we want to check. Okay, and then what we can do is, we can subtract that number. We can, from AX, we can subtract 0. That is, we are basically performing the number minus 0. Okay, this number minus 0, it could lead you to three different answers, right? It is equal to 0, or it is, uh, greater than 0, or it is less than 0. So if it is equal to 0, it means what? It means what? Number minus 0 is equal to 0. It means number is equal to 0, right? And here it is number minus 0 is greater than 0. It means number is greater than 0. Here number minus 0 is less than 0. It means number is less than 0. So if we subtract from that number 0, and then we see if the result is 0, or if the result is positive, or if the result is negative or not. And all these three things we can actually check. How do we know if the result is 0? Just by looking at the 0 flag. If the 0 flag is set, it means the result of n minus 0 is 0. How do you know if it is a positive number? The result of n minus 0 is positive, that is greater than 0, just by looking at the sign flag. If after performing this, this is not sum, I'm sorry. After performing this subtraction instruction, ax comma 0, if the result is, if the sign flag is 0, it means the result is positive. If the sign flag is 1, the result is negative. So that we know actually what is whether the result of n minus 0 is positive or negative or equal to 0. And once we know that thing, once we know whether the result of n minus 0 is 0, positive or negative, then we actually can conclude whether n is positive, 0 or negative. Okay, so more or less that is the concept. Now we are actually ready to write the code. How are we going to write the code? Okay, so for that reason, say for example, the number that we want to check, first, like this is how we do. We can assign a name to that particular number. It's like, say for example, you want to check if a given number is a prime number or not in C program. Then what we do, we declare a variable n, and then in that n we usually store that number, and that given number is represented by n. So the same thing here also. Say for example, this is a 16-bit number, and I call that number as a n. Okay, and 16-bit number, and that number is, say for example, uh, say anything. It could be, just for the time being I'm writing the number is equal to 3. Then we want to check if 3 is a positive number or it's a negative number or it is 0. Okay, so what we'll be doing is we'll moving these n to AX register first, and after that what we'll be doing is, as I said, this is just one way, huh? But this is not the only one way. So we'll be subtracting from this AX, we'll be subtracting 0. And after that, what we need to know is, okay, what is whether the result of this subtraction is positive, negative, or 0. These three things we want to know. Okay, if the result of this subtraction is positive, you see here, if we know what is the result of this subtraction is, immediately we know what is the value of this n, like what is the nature of the value of this n is, whether it is 0, positive, or negative. And as an output, what we might want to display is that if it is 0, we might want to display a 0 on the screen. If it is 1, we might want to display a positive on the screen. If it is less than 0, I mean, if it is negative, then we might want to display a negative on the screen. What am I saying is that, okay, that is our output of this particular program is actually, requires us to display 3 different strings, right? So I'm calling, say for example, string 1, like if the number is equal to 0, we might want to display this particular string there, say 0 terminated by dollar. Or I'm now writing the program. Okay, you should be able to connect the dots. Like you already, why am I writing these three strings? Because these are the possible three outputs there, isn't it? So positive, and the other option is negative. We might want to display them on the screen, so that's why I'm writing it. But still now I have not said anything about this jump. I'm just making the background ready, sort of. Now, okay, we up to this point we see here. If you look at this program, you should know, like, you basically you understand each and every line of this program more or less, right? Why we're doing. I mean, what exactly these different lines are doing. Up to this point, things should be clear. Now we are ready to move. Now, after performing this subtract instruction, what we are interested in, to know what is what is the nature of the result of this particular instruction. And right now we are interested in, if the result of this instruction is 0, it means what? We want to check if the 0 flag is set or not. Okay, and how we can do that? And if it is the case, then we want to display this 0 string on the screen. See here, these 3 strings we have to display at some point of time. Let's first display them. Okay, let me write it in this way. You will come to know. Just hold on, huh? Don't lose your patience. I mean, it will make sense in a moment. Although I am, like, covering, I'm just going not in a single direction. I'm just moving from here to there. But anyhow, it is going to make sense at some point of time. Just wait for another 2-3 minutes. It will make sense. Let's say we are displaying these. We have to display this 0 on the screen, the string 0 on the screen, str1 on the screen. How do we do that? We know that it is simple, right? First thing is that we have to load the effective address of string 1 to dx register. Sorry, to dx register. And then after that, we have to store these special number 09 in AH register. And then we have to call this interrupt service routine 20 int. We have to execute this int 21h. So this will display string 1 on the screen. And at some point of time, based on the input value or based on the number that we are checking, we might also have to display sometimes string 2 on the screen. And similarly, we might also have to display sometimes string 3 on the screen. These blocks of code we want to execute, but not always. When we want to, sometimes we might want to execute this block, sometimes maybe this block, sometimes might be this block. Okay, so for that reason, now when we want to display string 1, when both the numbers are same, I'm sorry, when the given number is 0, and when the given number is 0, if the result of this subtraction is 0, then the given number is 0, because if ax minus 0 is equal to 0, it means ax equal to 0. And how do we know if the result of this subtraction is 0 or not? Just by checking the value of the z flag. Okay, if it is in debug mode, then it is easy to actually look at this Z flag and see what is the value of this Z flag. That is okay, fine. But programmatically, how we are going to do that? That's the question, isn't it? So the question can be answered very easily if you know these conditional jump instruction called as JG or JZ. Okay, this is you'll read this instruction as jump if, see here automatically it is coming, jump if zero flag is on. It means what? Jump zero will be true. Jump zero will be true if Z flag is equal to 1. That is, see, JZ, this is a jump instruction actually, okay? JG will be, JZ, you might pronounce it that way. JZ will be true. This is true if Z is equal to 1. Jump on 0. I mean, if the zero flag is set to 1, it means if the result of the result of the previous execution is 0, then this jump jet condition will be true. Okay, now here see in the code how we can make use of it. Jump 0, I mean if the result of the previous execution, which is like subtract instruction, if the result of this particular instruction is 0, in that case which string we might want to display? We might want to display string 1, this particular code. So what we can do is we might see here jump 0. Since it is a jump instruction, here you have to write the location, like the the address inside the code segment where you want your instruction pointer to point to. So we have to like write the address of this particular instruction. But since we programmatically, how we can do that? We can, as we have done it in the previous example, we can assign a label. Say, for example, I'm writing here level 1, L1. So jump on 0, we want to transfer the control to L1. If zero flag is set, then we want to transfer the control to L1. It means what? This particular, immediately, if it is 0, immediately the control will come here and it will start execution from this point, okay? Done. Now, if it is 0, then it is the case. But what if the number is the result of this, execution is not 0? Two possible cases, right? If it is not 0, like see, here we have checked this one. If it is 0, then done. But if it is not 0, then there are two possible cases. Either the sign flag is on. Sign flag will be on if the number is less than 0, if the number is negative, or the sign flag is off. Now we have to actually look at the sign flag, and the same way you can do actually. See here, you can write jump and the name of the flag. Say for example, the sign flag is S flag. Jump on sign flag. It means what? If the sign flag is on. Sign flag is on. What does it mean? See, if the sign flag is on, here, if the sign flag is on in the sense like if the value of the sign flag is equal to 1, it means what? It is a negative. The result is negative. And if the sign flag is 0, it means the result is positive. Okay, so here what we want to do is, if we are checking like this, JS, when this JS will be true? JS will be true. JS will be true if sign flag is equal to 1. If the sign flag is set, then jump on sign will be true. Okay, and if that jump on sign is true, then where we might want to transfer our control to? See, if it is sign flag is true, in the sense what? Sign flag is true means the result is negative. So if the result is negative, we might want to display string 3. So here, so let me give it a label, say for example L2 here, and if this instruction is jump sign is true, then we would like to transfer the control to L2. Here it will display the number is negative on the screen. And then what else left is, see here, jump 0. If it is true, then it will transfer the control to L1. If it is false, then what will happen? Nothing will happen. It will simply skip this instruction, and then it will move to the next instruction. Jump sign, if it is true, then it will transfer the control to L2. And if it is false, then what will happen? Nothing will happen. It will simply execute the next line of instruction, which is L1. LEADXSTR1. It means now you can realize, like, you should realize now, okay, what happens? I mean, it should not come to L1 actually, right? It should go somewhere else, isn't it? It should not come to this point. So else part actually. Otherwise, you can directly write here jump. If it reaches here, see here, if this is also not true, this is also not true, then we know like which part of the code is to be executed. Which part? Say jump L3. And let's call this one as L3. Okay. See here, if it is, see, if jump 0 is true, if the 0 flag is true, then this part, the control will reach here and will start executing from here, here, and here. Now, again, you might be thinking, sir, what will happen after executing this instruction? Yes, you are true. After executing this instruction, the control will simply flow to this particular instruction, which we do not want actually. After executing this block of code, we want our control to go to directly the end of the program here. So what we can do is we can give here a name like terminate, any name. Okay, I'm just giving it a level, I'm calling it terminate. And then after execution of each block, what I might want to do is I might want to transfer it, see, unconditionally to terminate block. Now things should make sense to you. If it is, this is important actually, so that you understand. I just wrote it in one way, but there could be, you can write the same program in many different ways. I just, while explaining, automatically whatever the direction it is moving, I'm just writing it in that direction. Okay, but certainly you can write it in many different ways. I just wanted to show you the examples of these different jump instructions, how they work. Just wanted to introduce you these different types of jump instructions. But again, I just said to you, I just wrote the code here. I have not yet like shown you the output. Let's first see the output and then we can talk about it in some more details. Okay, so let's execute this program. Okay, first we'll be executing it directly and then we'll be executing in debug mode. Okay, let's first see what are the values. What is the number? The number is 3. So if the number is 3, then we should see a positive as the output. So let's see whether we get a positive as output or not. I'm writing tasm pp8.asm and then dlink pp8 and then pp8. It's a positive number. Okay, the output is right here. And let me change this number to a negative number, say -3. And then again, I'm compiling it, linking it, and executing it. It's a negative number. And then I'm writing here, say, a 0. And in that case, we should get here a 0, right? So that is the output. I mean, the program is showing us the right output here. Just have a look again. Certainly I'll be not, what does this means, right? If you have any confusion here, then please check my previous video. There I told you like how to display a string on the screen. Now here what we're doing is first we are storing the number that we want to check. Like what program we're writing this program. Write a program to check if the number is positive, negative, or 0. So for that reason, whatever the number it is that we want to check, we'll be copying it to AX register, and after that, that number will be subtracting from that number we'll be subtracting 0. Why I'll be doing it? Because if we know the result of that subtraction, if we know the nature of the result of that subtraction, like from there we can actually conclude the nature of this n actually. Okay, so and where we can from where we can know the nature of the result of n-0, just by looking at the flag registers. As you know, like this you should know actually, like when the zero flag is set, when the sign flag is set, and all this stuff. I already told you, but if it is not clear, just read any book or any related some related theory part somewhere, so that you get the idea when the sign flag is set, when the zero flag is set. Things are simple, straightforward actually. If the result is zero, result of the previous execution is zero, then zero flag will be set. If the result of the previous execution is negative, then sign flag will be set. Otherwise, they will be reset to zero. Okay. So based on that thing, what we did is we subtracted from ax 0, and then we check the we do some we write some conditional jumping there, and conditional jumping with respect to the flag register. So one conditional jumping instruction is jump 0 instruction. What does jump 0 instruction do? Does is actually it checks the 0 flag, and if the 0 flag is set, then only this instruction will be executed. Otherwise, it will not be executed. Okay, it will be skipped. Similarly, this is jump sign. This instruction will be executed, or this instruction will be true if the sign flag is set to 1. It means if the result of the previous execution is 0. Oh, sorry, if the result of the previous execution was negative. Okay, so that way, if the result of the if the sign flag is on, if the sign flag is 1, then this particular instruction will be executed, otherwise it will be skipped. And this is unconditional jumping. See here, what basically we are checking is, if they are equal, then go to L1 and display the code. So it will go to L1 and it will execute this line, it will execute this line, it will execute this line, and after that, after executing this line, certainly we do not want to execute this line. What line we want to execute? We want to terminate the program. So after executing this line, we'll be simply transferring the control to the this particular instruction. That's why we wrote here terminate. And then if it is the case, if it is 0 flag is set, then L1 will be transferring the control to L1, and that way it will execute, it will display 0 on the screen, because string 1 is 0 on the screen, and then it will terminate the program. Now, if it is not set, if the 0 flag is not set, say for example, the number is not 0, say for example, the number is 10. So certainly 10 minus 0 is not a 0, right? So in that case, jump 0 will be false. But if jump 0 is false, okay, no problem, nothing will happen. Then again, we'll be checking this jump sign or not. Like, we'll be checking whether the sign flag is on or off this time. So if the sign flag is on, we know that the result is negative. And if the sign flag is off, we know that the result is positive. So just checking the thing. So in this case, number is 10, so sign flag will be off. So see, if sign flag is on, then only it will transfer the control to L2. But if the sign flag is not on, then this instruction will simply be skipped. So once it is done, then the next instruction is jump 13. It means, see here, if the control reaches here, it means both these two conditions must be false. It means what? If the control reaches here, then certainly the number is a negative number. So that way, I'm just unconditionally this time, I'm transferring the control to L3 block here. And this block will start from here, and at some point of time, it will transfer again the control to terminate block, which is this. Okay, so more or less, these are the branching or jumping instruction. We might see here, these are conditional jumping, like jump 0, jump s. I mean, this jumping will happen, or this branching will happen only when this particular condition is true. And what condition this particular instruction is checking? It is checking if the 0 flag is set. The instruction that this particular instruction is the condition that this particular instruction is checking is if the sign flag is set. And here, this particular instruction is not checking anything, so it is unconditional jumping. So that's how actually things work. Now see, there this branching, there are many different ways we can do branching in 8086 program. I just have given you here an introduction. Like I showed you only a few of them. But see here, I have this Google Doc where actually I wrote, like, okay, these are different ways. See, these are different ways of doing unconditional branching. Say for example, call, return, jump, or loop. We have uh, this instruction I talked about. Very soon, maybe in the next video, I'll be talking about loop. and down like 3-4 videos I'll be talking about call or return. So right now we know only about jump. Very soon you're going to learn about this loop. As the name itself indicates, some obviously, all these names actually should ring some bell in your mind. But anyhow, I'll be talking about these other three very soon. But right now I covered simply this jump instruction. Okay, and then conditional branching. See here, a lots of conditional branching instructions are there. I have not talked about like many of them, but see, if you know how to use one or two, then you know how to use the rest of them. Okay, so which one I talked about? I talked about jump 0. See, used to jump if equal 0 flag is 1. See, if the Z flag is 1, then this particular jump instruction will be executed, otherwise it will not be executed. So if you write your jump instruction, that one I wrote in this way, I guess, jump on sign. See here, used to jump if the sign flag is 1. This if you write this instruction, that instruction will perform the branching only when the value of the sign flag is 1. If the value of the sign flag is 0, it will not perform that jumping. Now see here, with if JS is there, you will immediately know JNS is also there. This N stands for the negate. I mean the not. Here see JS, jump on sign, it is jump on not sign, the reverse one. Similarly, jump on 0 is there, so jump on not 0 is also there. Or jump on equal is there, jump on not equal is also there. Okay, you can go through this document. I'll be sharing it in the description section, and then from there you will get an idea about what are the different conditional branching instructions are there, and in what situations you might want to use them. But here in this part of the video, my main goal was to introduce you the concept of jumping, jumping and branching there. So in the next video, again, we'll be writing some more code. We'll see some more examples and we'll try to make use of some more conditional jumping instructions. Okay, guys, then hope you people have understood the concept that I tried to explain you. But if you people have any doubts or queries or anything, you people can ask me questions in the comment sections. Okay, guys, then see you guys in the next video. Till then, have a nice day.